Hello. Right, this video is going to be like sort of like a dumbed down, quick overview of electromagnetism, and this is probably going to be correct to degree level, I would say, but I'm going to keep it sort of really sort of dumbed down. Right, so there's three levels, or three sort of areas of electromagnetism, and the first is the electrostatic force. Right, and this is just the force that exists between all charged particles. So this is the force that makes a proton attract an electron, and also the force that make two protons repel each other, or just similarly charged particles. Right. Secondly, we have the magnetic force. And to explain what the magnetic force is, basically to degree level, just without all the maths and things and calculations. So if a charged particle is moving and not just stationary, it also generates a magnetic field. In addition to the electric field, it generates a magnetic field as well. Right, and this is why electromagnets are a thing. If you pass a current through a wire, because we have moving electrons in the wire, the electrons are moving, they're moving charged particles, so they make a magnetic field around the wire. With magnets, it turns out magnets, which are made of magnetic materials like iron or cobalt, these elements, they have spinning electrons inside them. Now, because the electrons are spinning, they're in motion, they're moving. Therefore, each electron that's spinning acts as one tiny little magnet. Right, so magnets have these spinning electrons inside them. And when you have a magnet, it basically means all the electrons are spinning in the same direction. So you get one big magnetic field. Sometimes you have a lump of iron, but it's not a magnet, because there's no overall magnetic field, because essentially within a random lump of iron, all the electrons are spinning in random directions. So you might have one electron that's like spinning in the up direction, let's say. Then you have an electron which is spinning in the down direction right next to it. And the magnetic fields cancel each other out. So when all the electrons are spinning in random directions, those mini magnetic fields cancel each other out and you get no magnetic field overall. In order to turn a lump of iron into a magnet, you have to place it inside a stronger magnetic field. And then what happens is all the electrons align to that magnetic field and they start spinning in the exact same direction. And then that's when you get a magnet, when basically all the electrons are spinning in the same direction. Not actually all of the electrons, but more than the majority of electrons are spinning in the same direction, so you get an overall sort of consensus, you get an overall magnetic field. Right. And then this is beyond GCSE, but electromagnetic waves. Right, electromagnetic waves are caused by an accelerating charged particle. So when you take a charged particle and you accelerate it, not all of the energy goes into accelerating that charged particle. Some of the energy goes into emitting an electromagnetic wave. And this comes from one of Michael Faraday's laws, and he discovered this in like the late 1800s. And he wrote these equations and calculations down, and they showed that a changing electric field causes a changing magnetic field. And a changing magnetic field causes a changing electric field, which will then cause a changing magnetic field, which will cause a changing electric field, and so on and so on. It's like a chain kind of like reaction, if you like. It's like self-generating. It never stops. So you get this electromagnetic wave, which propagates outwards into all of space. And how do you make a changing electric field? Well, I guess if you think of like a proton, where you have all these field lines coming out from the proton in all directions, as soon as you move that proton, you've changed the electric fields, because now the electric field lines are now originating from somewhere else. Hence why an accelerating charged particle causes electromagnetic waves, essentially with all that information linked together. Yeah, so how do we actually make electromagnetic waves? Well, like, what we do usually, if we're talking about radio waves, we take a piece of metal and we put an alternating current through it. And with an alternating current, right, the electrons go one way and then they go back the other way. And they reverse back in the other direction and they go back and forth constantly. So what happens is, so electrons will be moving in one direction and then they have to come to a stop. Now, when an object deaccelerates, that counts as negative acceleration. So that causes an electromagnetic wave. And then they accelerate again back in the opposite direction. So then when they're accelerating in the opposite direction, they also emit an electromagnetic wave. And essentially the electrons are just like constantly accelerating back and forth. So they're constantly emitting electromagnetic waves. And then, like our sun generates electromagnetic waves. And that's because of the nuclear fusion reaction going on inside the sun, which essentially causes nuclei to accelerate, because there's so much energy released in a nuclear fusion reaction. The newly formed nucleus will come flying off and it will undergo massive acceleration. And then because you have all these charged particles accelerating all the time in the sun, it causes an emission of electromagnetic radiation. Right, and then the electrostatic force and the magnetic force, this goes to degree level. They're actually the same force at degree level in physics. Sometimes you'll just refer to both of them as the electromagnetic force, because it turns out that the magnetic force is kind of like the electric force, but from a different frame of reference. And this is all about this comes from like Einstein's ideas when he shows that when a charged particle, or even you or I, are moving at very high speeds, the way we experience space and time changes. The way we experience space is different and time slows down. Same for charged particles. When they're moving at high speed, the way they experience space is different. And since the electric force operates in space and time, the distortion of space-time that's experienced by a charged particle changes the way they experience the electric force. So what physicists do is they invented the magnetic force just to easily explain like how basically the electric force has weird effects. And it's just a lot easier to talk about magnetic fields essentially, and it kind of skips like the complicated stuff of what actually goes on with the theory of relativity. I'm actually going to link a video by Veritasium if you're sort of interested in this idea, where his video is literally about how the magnetic force is just the electric force from a different frame of reference. It's very important to know that for any students who are sitting their GCSEs in the future, you're not going to get away with calling everything the electromagnetic force. You need to just know, you need to use the correct terms, and you need to call some things the electrostatic force and some things the magnetic force. The magnetic force will only arise in two instances in your exams. So one instance is where they're talking about magnets, and the other instance is where they're talking about electromagnets. If you don't see the word magnet in the question, you're not going to be talking about the magnetic force. And just to clarify, if you have a question which is talking about a rod has been charged up and it's gained a charge, you're going to be talking about the electrostatic force. Anything on the topic of static electricity is going to be the electrostatic force. You can kind of get away with calling the electrostatic force just the electric force, but electrostatic force is certainly the term to learn for your GCSE exams. Um, I hope this was like interesting / helpful. I'm going to sign out. Until the next one.